All right, so we just talked about descriptive statistics. So we are going to very briefly touch upon inferential statistics. I think there's about 9 or so slides in this presentation. Again, there's great software and resources out there, and I know none of you, I can't imagine a situation where any of you would need to do statistics by hand or even, yeah, math. Um, all right, so a couple of important things to know. So inferential statistics are statistics that are used to infer or make meaning of the data that we collect. And there's 3 main goals of inferential statistics, depending on the research question. So these are statistics that look at or assess a relationship or a correlation between 2 variables, statistics that assess for a difference among groups or among variables, and statistics that look at whether one variable predicts another or one variable predicts many other outcomes. So the type of statistical test that you choose will depend upon a few different factors. So first, the type of data. So we talked about the levels of measurement in the last lecture. So this is, ordinal data, ratio data. This is going to inform the type of statistics that you can use. It will also depend on if your data is parametric. So if your data is normally distributed, or if it's skewed, if it has a high level of kurtosis, you may need to use a non-parametric statistical test. And then your statistics will also depend on the number of independent variables in your study. And I uploaded a really, really nifty flowchart to the module for this week that goes through, you just answer questions about your research goals, how many independent variables you have, whether your data is parametric, I believe it also covers as well. And then it kind of spits out at the end a test that you can use for your statistics. So I want to talk about type 1 and type 2 errors, and we touched upon this during one of the earlier lectures. But basically, when someone is conducting research, they're going to assume before they run their tests, they're going to assume that there's no relationship or no effect among the variables in the study. This is referred to as the null hypothesis. So researchers will then formulate an experimental hypothesis and then test their hypothesis using statistics. If the null hypothesis is true and researchers find that there's a relationship, then they make a type 1 error. All this means is that basically the researcher is saying that there are results, there's a relationship, there's a predictive relationship between variables that is not actually there, it's not actually real. If the null hypothesis is false and researchers do not find a relationship, then they make a type 2 error. And all this means is that the researcher had missed a significant result that is actually present. And that's called a type 2 error. So effect size. Effect size is basically an assessment of how attributable the effects of the independent variable are on the dependent variable. And you'll see among research articles that you look at a common kind of statistical test for effect size is the Cohen's d, or just d, a d value. Then we have confidence intervals. So confidence intervals are used because we have to understand that a sample is not necessarily representative of a population, like we talked about in earlier lectures. We hope that it represents the population, but we don't know that for certain. So confidence intervals can identify kind of a range of scores that have a certain likelihood of containing that population mean. So that true score falls somewhere within that range. So for example, let's say we have a participant that receives a score of 90 on a standardized test. And we say that the 95% confidence interval provides a range to us of scores between 87 and 93. So basically all this means is that there's a 95% certainty that that participant's true score falls within that range. Then we have this idea of statistical power. Statistical power refers to the probability of correctly rejecting the null hypothesis when it should be rejected. So getting it right, basically. And there's a few different factors that kind of play into statistical power. So we have alpha. These are p-values. Basically, the smaller the p-value, the higher the bar for statistical significance. So we have, for example, you'll see in research studies, p is less than 0.05, which is a pretty standard test that's used for significance. People will usually say that they're significant results if they use that p is less than 0.05. P is less than 0.01 is going to be an even higher bar. So that's an even lower percentage that the researcher is saying that this was by chance. These findings were by chance. Then we have effect size, like we just talked about, and then sample size. So basically the bigger the sample, the higher the number of people in the study, the more likely it is that it's going to be representative of the population. So let's talk quickly about p-hacking. There's a video on the module for this week that gets into more about p-values. I think it explains it very nicely. And then this issue of p-hacking. Basically, this is a big threat to validity. It's a big problem. It involves intentionally or unintentionally manipulating analyses to find a relationship or effect. And we can think of this in an analogy like even a broken clock is right twice a day, right? If we look hard enough, if we conduct enough analyses, we're going to find something that's there but really isn't meaningful. A relationship that just kind of is by chance. So some examples include when researchers continue to gather data from participants until they reach statistical significance. So they kind of modify the duration of their study to get results that are significant. It could also include running multiple analyses that stray from the original research question. So if you're running, 20 correlations among variables, you're probably going to find something. You may find something, but is it meaningful or is it just by chance? How can we protect against unintentional p-hacking and address this issue within the field? So the video talks about this, but pre-planning research with a set sample, planning a period of data collection. So we know we're going to start collecting data on, June 1st, and we're going to stop on, October 31st, and whatever data we get in that period of time, that's what we're going to use. We're not going to extend it any longer than that. We can also use pre-planned analyses that will answer the research question. And if someone's running many analyses, maybe because they're doing an exploratory study, they can use procedures to kind of raise the bar on what constitutes significance. In one example, this is very, don't need to know this, but an example of this would be the Bonferroni correction. So in my dissertation, I ran multiple correlations using non-parametric tests. So the tests were less powerful. It was a small sample, and there was a lot of different tests going on. And so I used a Bonferroni correction to kind of account for some of that possibility of finding having a significant finding that wasn't actually there. And indeed, there were significant findings. And then once I used the Bonferroni correction, the significant findings were no longer significant. So yes, it is what it is. And then, of course, we talked about replication. So, another researcher conducting a similar study to try to see if, is this finding actually true, or was this just by chance? So just real quick, help, what is math? Oh my goodness, I felt this way starting graduate school. But there's a few different kind of things I would recommend if you're running analyses or conducting a study, is to consult with professors and knowledgeable peers. So these are folks who've done research. They can kind of coach you through some pitfalls and help you figure out what kind of data you have. If you have nominal data, ordinal data, interval, or ratio. use online resources. There's so much free content on the internet right now for various learning styles, various different ways of explaining these concepts, and it's just excellent. There's also some services that cost, they're either free, I think, for a period of time. Maybe there's like a free trial, but then you can pay for really, really good services that will offer kind of a step-by-step guide on which statistics to select for your variables and what assumptions about the data have to be met. So is it parametric, not parametric? And then once you run your analyses, how to go ahead and interpret those results. And then practice using statistics software like SPSS. Excel has some of those features as well, but SPSS is one that's used frequently for research in professional research and dissertations, etc. So there's help out there. You don't need to know all the things. Just want to say that. All right. Thanks, everyone.